This video will introduce the topic of the quadratic formula and quadratic inequalities. The learning outcomes for this topic is to use the quadratic formula to solve quadratic equations, to use a discriminant of quadratic equations to determine the nature of its solutions as well as its graph, and to solve quadratic inequalities. When I teach college algebra in a face-to-face class, we derive the quadratic formula together using the completing the square method. If you are interested, you are more than welcome to view a separate video I found on YouTube doing the derivation. However, I am sure most of you are familiar with the quadratic formula as x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. I do the quadratic formula a little differently, but very effectively using the discriminant. I will show you my method, and you are more than welcome to use the formula the way you know best. Before we can use the quadratic formula, we need to make sure that our quadratic equation is in the standard form ax squared plus bx plus c is equal to 0. Once this is done, I like to look for a, b, c, and big D, where big D is b squared minus 4ac. It is denoted with the capital letter D and represents the discriminant of the quadratic equation. Now I am able to substitute the values of a, b, c, and big D into the formula x is equal to negative b plus or minus the square root of big D all over 2a. I am not sure if my math lab will allow you to enter the plus or minus. In any case, note that you will get two answers depending on the value of D. Your answers are in the form of the solution set of negative b plus the square root of big D all over 2a and negative b minus the square root of big D all over 2a. I stated that your answers depend on big D, the discriminant. If big D is a positive number, D is greater than 0, we can take the square root of big D and get real values. If big D is a perfect square, such as 4, 9, 16, 25, etc., when we take the square root of big D, I will get a whole number. This means that our solutions for x will be two real and rational solutions. However, if big D is not a perfect square, such as the number 5 or 12, we can still get the square root of this number and it will be an irrational number. This means that our solutions for x will be two real and irrational solutions. If big D is 0, our quadratic formula reduces from x is equal to negative b plus or minus the square root of big D all over 2a to just x is equal to negative b over 2a. This means that our solution for x will be one real and rational solution, the value of negative b over 2a. If big D is a negative number, where D is less than 0, we can take the square root of big D, but we have to use our knowledge of complex numbers to do so. If big D is negative 16, when we take the square root of big D, and we get a whole imaginary number, in this case 4i. This means that our solution for x will be two complex and rational solutions. However, if big D is not a perfect imaginary square, such as negative 12, we can still get the square root, and it will be an imaginary irrational number. This means that our solutions for x will be two complex and irrational solutions. I give this exercise to my students in my face-to-face class. I ask them to sketch the graph of the equations. Here I have added the graphs for you to see. Then I ask them to complete the table using the value of big D and the number of x-intercepts found in the graph to make a conclusion that I will explain shortly. You may want to pause the video here to see if you can make the correct conclusions before continuing the video. I like using the discriminant to predict what I should expect when using the quadratic formula. I also like to use it to let me know what the graph will look like. For example, if big D is positive, I know I will get two real solutions. Rational or irrational does not matter, and this means that the graph will have two x-intercepts. However, if the solutions were rational, then the equation was actually factorable, which means I could have factored the equation to find the x-intercepts. the reverse is also true, that if the solutions were real but irrational, I would not be able to factor the equation. If big D is 0, I know I will get one real rational solution, and this means that the graph will have one x-intercept. This means that the vertex of my graph will be on the x-axis. The graph can open up or down since that depends on the value of a, the coefficient of x squared. This is what we learned in Unit 2 about vertical reflections. If big D is negative, I know I will get two complex solutions, and this means that my graph will never touch or pass through the x-axis. This means that the vertex of the graph is either above the x-axis and opening upward, or the vertex is below the x-axis and opening downward. In either case, the graph stays away from the x-axis. The conclusions are that if D is less than 0, the graph will not have x-intercepts and will not touch or cross the x-axis. If D is equal to 0, the graph will only touch the x-axis and have one x-intercept. And if D is greater than 0, the graph will cross the x-axis twice, and it will have two x-intercepts. Finally, the last learning outcome states that you will need to solve quadratic inequalities. Before going through the steps of doing this, let me first talk a little bit about the whole graph inequality. For example, let's say we have the inequality of y is less than x squared minus 4. We know what y is equal to x squared minus 4 looks like, and here's a quick graph. Now we need to see if we need to shade the inside or the outside of the parabola. In other words, we need to find all the points that satisfy the inequality that y is less than x squared minus 4. When we did linear inequalities in Unit 1, we shaded all the numbers on the number line that satisfied the original inequality. We tested values in the original inequality to see what side to shade. For our parabola here, let's pick a point in the parabola, such as the point 0, 0, and check to see if it works. 0 is less than 0 squared minus 4. So is 0 less than negative 4? Remember, this also says, is negative 4 greater than 0? The answer is no, so we will not shade the inside of the parabola. Now let's pick a point outside of the parabola, such as the point 6, 0, and see if it works. 0 is less than 6 squared minus 4, or 0 is less than 32. This is the same as 32 greater than 0, which is true. So we need to shade all the outside points. When we are solving our quadratic inequality, we are only interested in the x-axis. So for our example, we see that on the x-axis, we shade it from negative infinity to negative 2, and from positive 2 to positive infinity. And we can note that in interval notation. Notice that I do not include the x-intercepts in our intervals, since the original equation did not have an equal sign. If it had been greater than or equal to, or less than or equal to, then the x-intercepts would be included as part of the solution. Let's talk about some steps to use to solve quadratic inequalities more efficiently. First, we need to solve the associated quadratic equation to find the x-intercepts. This means we will need to solve quadratic equation using the methods that we have discussed, such as factoring and setting the factors equal to 0, square root property, completing the square, and the quadratic formula. Once you find the x-intercepts, graph them on the number line representing the x-axis. Use closed circles if the equation has less than or equal to, or greater than or equal to, and use open circles if the equation only has greater than or less than. The x-intercepts should divide the number line into 1, 2, or 3 sections. Test an x value from each of the sections on the number line. The points will be some value for x from the sections on the number line, and the y value is 0, since we are testing points on the x-axis. Plug these points into the original inequality and see which points make the inequality a true statement, and shade the true sections. Notice that I mentioned that the x-axis could be divided into 1 or 2 or 3 sections. If you find two x-intercepts, the number line will have 3 sections. one on the left of the leftmost x-intercept, a section between the x-intercepts, and one on the right of the rightmost x-intercept. If you find one x-intercept, it will divide the number line into two parts, to the left and to the right of the x-intercept. If you do not find a real solution, the number line is not divided. Either the number line is blank and the answer is no solution, or the entire line is shaded and the solution is all real numbers. One cool solution to find is one where there is only one x-intercept and it is a closed circle on the number line. This is found when the inequality is less than or equal to, or greater than or equal to, and the shading is inside the parabola, so that no other part of the number line is shaded. If the inequality does not contain the equal sign, none of the number line is shaded, and the answer is no solution. This concludes this video.